Hi, I'm sorry for the trouble I had with the first live streaming attempt. To anticipate with the connection and the location, I thought it was silent. So now I'm gonna have my second try for live streaming. We need to push through with this so that you can be helped chemistry examination tomorrow. Now, before I'm gonna start with anything, can you please comment in this live streaming video if you can already hear me? I need your help to tell me whether you can hear me right now. Streaming review video. Comment, and I need you to tell the others that we're online right now, that we're streaming live, so that you can ask questions right there and then. Don't depend that you can just watch the video later. It's better that you watch it right now so that you would know where you are, what your weaknesses are, so that you can we can remedy whatever difficulty you have. And right now, I hope that you can see you can already see the screen. You have test 3.1. Hello, Jean. Please tell your classmates that we're online right now. Can you see the screen? Can you see the table of test Jean and Cherry? Now, there's some okay. You can't see the screen, Cherry. Wait. Um, mhm. Okay, wait. Right now, can you see that? Can you? Okay. I'm trying something right now. I hope you can already see by now the table. The values of temperature, volume, pressure, and number of moles. I hope you can see them already. Okay. So let's view with test 3.2 of gas laws. Now it's better that you have your test paper with you so you'll know what your mistakes were and you can correct them as I discuss the items. Now this won't take long. You can ask questions right away in case you have some difficulty. Okay, so with this table in the exam, even if all the values are given, it doesn't mean that you can use any gas laws that we have, particularly all combined gas laws or the ideal gas law. Remember that in this particular table, you can cancel similar values. So if you can cancel similar values, that means those are constant values. If they're constant, that means they're not part of the equation anymore. Now let's recall the gas laws. The first 5 gas laws that we know, the ones with the 1 and 2, the one with the initial and final are the following. We have Boyle's law. Write that down. Or may I just guide you through using the ideal gas law, because the ideal gas law will give us the idea of all the gas laws actually. So our ideal gas law is PV is equal to nRT. Now, in tomorrow's exam, that only 3 gas laws will come out in the problem solving, particularly ideal gas law, Dalton's law, and Graham's law. But it doesn't mean you will forget the other laws, because you need to remember relationship. So for now, for today, we will just be using the ideal gas law for us to recall the basic gas laws, the relationship. So let's just use PV is equal to nRT, because we're going to see everything here. So let's start with the highlight of P times V. Together already, that's our hint that that's your Boyle's law, that your PV are together, so that means we can derive P1, V1, V2. Okay? And that's the only law that has inverse relationship. If it's inverse relationship, all the ones together in the left and all the twos together on the right. So that's the first law. Law. Now, Charles' law is V. Now, T is on the other side, so that means you need to put that under here. So, if you will put that under here, V and T is on the other side, but it is numerator, denominator. Now, you know that relationship. 1 over T1 is equal to V2 over T2. If the equations are directly related, that means if one increases, the other one also increases. So that's the format, which is very different with Boyle's law. Just being multiplied. But in Charles' law, because they are directly proportional, that means the two variables have to be have to be divided. So all the ones together still, but divided, and all the twos together on the other side, but divided also. And because it's temperature, we have to make it in Kelvin unit. Next is Amonton's law. You know that Amonton's law T here, which is more or less the same with Charles's law. So when we write Amonton's law, the same pattern with Charles over T1 is equal to P2 over T2. Still, it has temperature, but again, the relationship is just the same. They're directly related. So that means you need to divide variables there. And once you use that, you may just cross multiply that, in which 1 and 2 will be on the same side, and the other side will also be 1 and 2. Difference between your direct relationship and the only inverse relationship. Okay, so far so good. I hope that you are listening to me. And then lastly is your V and N. Now V and N is what we call the Avogadro's law, relationship of volume and N. Now N is on the other side. That means you need to divide both sides by N. So that means when you transfer N to the other side, that's going to be V, in which that's still going to be the same. V1 over N1 is equal to V2 over N2. So this is your Avogadro's law, in which V and N also have direct relationship. So you see that there are four laws that we've discussed, and 3 of that, Charles' law, Amonton's law, and Avogadro's law, have direct relationship, and only Boyle's law relationship. So take note of the format and take note of the variables that you are studying, because when you are asked to identify laws, gas laws tomorrow, you need to know what variables are involved in that particular law. Boyle's law again, which is inverse relationship. Charles' law, direct relationship of V and T. Amonton's law, direct relationship of P and T. And volume and amount in moles, also direct relationship, which we call the Avogadro's law. And then we also have the combined gas law, which combines Boyle's, Charles, and Amonton's law, in which we will have 1 V1 over T1 is equal to P2 V2 over T2. So that's your combined gas law. But anyway, since only 3 laws will come out in the problem solving, remember for this are the concepts and the variables for these 5 laws that I'm discussing. And then I'm gonna give some other problems for the other 3 laws. Miggy, we cannot have index cards tomorrow. I am giving you only 3 gas laws problem solving. That means for these, the ones that I'm discussing right now, the Boyle, the Charles, the Monton, the Avogadros, and the combined gas law, just remember the variables involved. Just remember which I've shown here. So I hope you will not find this hard to remember. So as what I have said, just look at your ideal gas law to NRT, and you would see there all the variables to know for every law. Okay? So for the table here, the approach is you just cancel out what you don't need. So you cancel out similar values. Like for example, here 2 moles are canceled and then 1 atmosphere. That means you're left with volume and temperature, in which volume and temperature is just Charles's law. Okay, that easy. And so when you do calculation for that, all temperature has to be in Kelvin. So recall a bit of your conversion factor for temperature. Now, don't dwell too much on the conversion factor, but let me just give you the conversion here. 70 degrees Celsius should be 343 Kelvin. And your 200 degrees Fahrenheit, that's equivalent to 366.48 Kelvin. Now, you may pause this for a while, get your notes on how to convert Fahrenheit. Now, I'm giving you the answers and just proceed there. Okay? So I hope that you're getting it. Remember, it's always 273.15. If you're converting from Celsius to Kelvin, and from Fahrenheit, you need to convert Fahrenheit to Celsius first before you add 273.15 Kelvin. That's why it's 366.48. So I won't anymore dwell too much on the calculation of this because again, a few of that will come out. So I'm just teaching you the approach if ever you'll be asked for what type of law. The second is you can cancel out 12 degrees Celsius and you can also cancel out the 2 moles. Okay, so cancel out N and T, so that means N and T are the same. That means we're left with P and V. And if it's P and V, that means it's just Boyle's law. Okay, the third one is we can cancel out volume, so you have 0.5 liters, and we can also cancel out amount, which is 1 mole. So we're left with pressure and temperature. Pressure and temperature is just a Monton's law. So we can just use P1 over T1 is equal to P2 over T2. That's a Monton's law. Fourth is we can cancel out temperature. They're the same, 50 degrees Celsius, and pressure of 1 atmosphere. So that means we're left with volume and amount. So volume and amount is just purely your Avogadro's law. Okay, V and N. And lastly, we can cancel out 0.5 moles, and that's all. The others are different. And if all are different except for the mole, that means it's a combined gas law because P, V, and T are all changing. Nicole, tomorrow you will be bringing your periodic table because you need the mass for molar mass calculations, for ideal gas law and Graham's law. And also Dalton's law, you would need that, okay? So any questions with the table so I can proceed to the real problem solving now? Any questions so far for those who are viewing this? So again, not so much trouble with the computation of Charles, Boyle, Monton's, Avogadro's, and combined gas law. It's conceptual. All you need to know is the variables involved in that particular law. Do not mix up the laws, okay? Do not mix them up. As long as you know that Charles is always V and T, Boyle's are P and V, Monton is P and T, Avogadro's is V and N, and combined gas law are PV and T. Okay? I hope hope that is clear to you. Now absorb that for a while, because conceptually you need to remember all the laws. Okay, now we're ready to take up the problem solving, focusing on 3 again: ideal gas law, Dalton's law, and Graham's law. Okay, now when I say ideal gas law, this includes density. Okay, so let's start. One is ideal gas law, but this number 1 problem, let me just explain a bit, even if it's not related to the 3 laws tomorrow, but let me just explain a bit. You're given an ideal gas that has a temperature of 15 degrees Celsius and a radius of this, 1.18 cm. And then the gas is heated at constant pressure to 88 degrees Celsius. Determine the radius. Now, examine the variables that you are involved. The variables is you have T and you have radius, in which you can convert to volume. That's why you're given the formula. So you can convert the radius to volume, and then you have heated it to another temperature T2. So this is your T1. Again for radius, the next radius 2, and that's radius 1, in which radius 2 may come from volume 2, right? And the radius 1 will have your V1. So in this problem, if you'll be asked, not necessarily, if you'll be asked, what law governs this particular problem, analyzing what you're given, converted to V, temperature is there, T1 and T2, and you're asked for another radius, which is related to another volume. So you're just asked for 2. I mean, you're just involving 2 variables, volume and temperature. That means number 1 is all about Charles's law. It talks about your Charles's law, gas law, because you're just involving 2. So that means if you're going to solve that, that's going to be your V1 over T1 is equal to V2 over T2. And remember that temperature has to be in Kelvin. So I won't dwell too much on that anymore. There will be no computations about Charles' law tomorrow, but I'm just using this so that you'll know conceptually how to determine what law. Okay? Let's proceed to the second problem. The second problem is all about density. What ammonia gas? What is ammonia again? Ammonia is NH3. So what is the density of ammonia gas at 2 atmosphere pressure and temperature of 25 degrees Celsius? So you are asked for density. Now, density, formula of density is pressure times molar mass over RT. Now, I've shown to you the conversion of that already. I hope that you can still remember the conversion of, from ideal gas law to density. For now, I'm just going to go directly to the formula of density. So that's P times mm molar mass over RT. So in a way, we can just solve this right away. Pressure, because this is from ideal gas law, it has to be in atmosphere. So that means that's correct already. The unit is okay. So that's 2 atmosphere. NH3, that means you need to have your periodic table. And again, you're allowed to bring your periodic table tomorrow. So NH3, that's 1 nitrogen and 3 hydrogen. That means the mass is 17.04 grams per mole. And then R is 0.0821 liter atmosphere per mole. And then, of course, your T has to be in Kelvin all the time. So that's 25 plus 273.15, and that becomes a Kelvin. So may I suggest that you may go right away to your calculator so that you can already get the accurate answer without rounding up nor rounding off. Direct answer, and then cancel out units. So that means the default unit for density should be grams per liter. Now let me show you How will it be grams per liter? Let's cancel out. Cancelled out. Kelvin gets cancelled out. Mole gets cancelled out. So you're left with gram on top and liter below. That's always the default unit of density. So therefore, putting that in the calculator, and I hope you have your calculator with you now, density of ammonia gas is 1.39 grams per liter. Right. Please comment if you have some questions, and if you find this video helpful for you. If you have some questions, please do so. For those who have a different set of exam, it's more or less the same way. Just make sure that you substitute the right values, okay? But the formula we're using is just the same. Any questions about density? So density, again, it's P times molar mass over R times T, in which temperature has to be in Kelvin all the time, pressure has to be in atmosphere all the time, because density's formula came from ideal gas law. And again, memorize, please, the value of your R. Got this? Okay, now it's time for me to erase number 2 so I can proceed to problem number 3. Number 3. Number 3, it says, a container with a volume of 71.9 ml, 71.9 ml, water vapor. Water vapor is still H2O. Take note of that. That's still water. At a pressure of 10.4 atmosphere and a temperature of, that's 465 degrees Celsius. How many grams of the gas are in the container? That means you're asked for the mass. Now, mass are always related to molar mass and your mole. We can go direct calculation for mass, but I suggest that we can do it one by one, because you don't have grams, but you know that there's N. And from ideal gas law, PV is equal to nRT, then we can just solve for N right away, in which N is mole all the time. And once you get the mole, you can just convert it to grams right away using the molar mass. So that's going to be PV over RT, in which we have the values there. So P is 10.4 atmosphere. And then your volume should be in liters, because this is ideal gas law. So that's divided by 1,000. So that's 0.0719 liters over 0.0821 liter atmosphere per mole Kelvin. And then your temperature is in Celsius. So the 465 has to be added by 273.15 Kelvin. Okay, then you can input that to your calculator and make necessary cancellation of units. So atmosphere gets cancelled, liter gets cancelled, Kelvin gets cancelled. So you're expected to have the unit mole because you're looking for N. We can get the answer of N to be 0.01. I'm just gonna put all the values lang ha. You have it to decimal places. 0.0123 mole. And how do we convert again from mole to gram? That means you need to get the molar mass of water, which is 1 oxygen and 2 hydrogen. That means you have 18.02 grams. Can you get the grams? So that's 1.22 grams of water. Okay, so that's it. We got it already. This will clarify some of your questions from your result. Okay, you may pause this for a while if you need to absorb that. And please ask questions while I'm still here. Just erase the solution of problem number 3. Okay, let's go now to this one. This is the hardest. A lot of not get this particular problem about identifying the molecular formula of a compound given some variables here. It's tricky. This is a very problem. Let me explain to you why. You have 0.580 gram sample of a compound containing carbon and hydrogen only. Carbon is 0.480. 0.02 Nigi comes from the periodic table, H2O, 2 hydrogen, 1 oxygen. Okay, so going back to the problem. The 0.580 gram sample contains carbon and hydrogen, in which you're given 0.480 grams of that is carbon and 0.100 grams of that is hydrogen. That's not H2, that's not also carbon, just carbon. It's not about gas, but it's the component. Then, there's something that happens to this particular compound. Maybe it has turned into gas. Because in the second sentence, it says that with this compound, at STP condition, 6 ml of that gas has a mass of 0.087 grams. Of the choices that I'm giving here is the true molecular formula of the compound. When you're asked for something like that, the best approach is to get molar mass. That you know the molecular formula, the easiest way is to look at the periodic table and get the individual molar mass, because molar mass can be calculated in gas laws, particularly in, correct? In ideal gas law, in density. So the first thing is you need to calculate for the individual molar mass here, and whatever matches with your molar mass calculation, then that becomes your answer. So CH3, I hope that you have your periodic table with you. CH3 has a molar mass of 15.04 grams per mole. C2H6 is 30.08 grams per mole. C2H5 is 29.07. C4H10, sorry, it's not aligned anymore. C4H10 is 58.14, and the last is 60.16. Correct? So just align that, okay? That's in order. So this is CH3, this is C2H6, C2H5, C4H10, and C4H12. Please, for those who forgot how to get molar mass, look at your periodic table and please to multiply the mass of that element by its subscript. Then you add it to the product or the sum of the masses of the next element. So that's a molar mass. Then what is the equation that we're going to use to solve for the molar mass? Now, let me just go to ideal gas law right away. So ideal gas law is PV is equal to nRT. And you know that N, mole, came from mass over molar mass. That's how we get mole. N times RT. So now we can get molar mass, right? We can get this. We cross multiply that. So when we get molar mass, that's going to be molar mass M, small m, that's mass, over PV. The molar mass here will cross multiply to PV, and you need to get rid of PV, so that means you divide that. So now we are given the mass. Now which mass will I use? Will I use the sample? Will I use the 0.480, the 0.1, or I'll use the one at STP? It has 0.087 grams. Now, the first sentence is actually a trick. You may use the first sentence values to get EF, in which you'll get a different answer in getting the empirical formula. But that's not what we're getting. It says that you need to give the molecular formula. So that means the safest mass that you need to use is the mass of the gas, which is 0.087 grams. That's what you need to use, not this. The first sentence again is good for the calculation of the empirical formula, but not for the real molecular formula. So that means we're going to use all the values at STP. That means we're going to use 0.087 grams, of course 0.0821 atmosphere per mole Kelvin, and then T, because it's STP. What is STP again? Standard T is 273.15 Kelvin divided by P in STP, remember, is 1 atmosphere. Is 33.6 ml, that has to be in liter, so divided by 1000, so that's 0.0336 liter. Okay, let's cancel out the units first. So that means we cancel out atmosphere, liter is cancelled out, Kelvin gets cancelled out, and so we're left with grams per mole, which is the correct unit of molar mass. In the calculator, for those who are online right now, can you please comment what's your answer when you input the values in your calculator? Let me just pause for a while and let me wait for your answers. Get your calculator, please, and input the values. What's your answer? I hope you're still with me. 0.087 times your R times 217. Please parentheses everything, then divided by, of course, that's just 0.0336 because that's going to be multiplied by 1. Mass is, how come there are no comments? Mel, Miggy, Regine, Cherry, can you please comment your answer? If you're really studying there, if you're really having your notes and your calculator ready with you. Correct. So you get around 58. That's correct. Around 58.07 grams per mole. Thank you for that. Which is the nearest compound that has around 58 molar mass value is your C4H10. Correct. Thank you, Cherry and Regine. So you got 58.14, around 58. So that means you're already able to get the true molecular formula of the compound. So again, let me just clarify this. If you're asked for the true molecular formula of the compound and you have choices, just get its molar mass. That's the safest way. Don't anymore go back to calculating EF. That's correct, but you can't proceed if you have empirical formula because you're not given mass. So you can't really proceed. So the best way is you use your ideal gas law to get molar mass. Okay, so let's proceed to the next problem, the last problem in your test. This is now about Dalton's Law, which will also be part of the problem solving tomorrow. Let's begin with the last problem. And I have some more problems that we will discuss today. Okay, so here, a mixture of 90 grams of methane gas CH4 and 10 grams of argon has a pressure of 250 torr of constant temperature and volume. Constant T and V, that means it's just Dalton's law. And what is the partial pressure, therefore, of CH4 in millimeters mercury? Miggy, yes, you can, because my only rule is up to 2 decimal places. Okay, I hope I answered you. So if you're asked, if the problem is about mixture of gases, and you're asked for partial pressure, that means this is all about Dalton's law. So we have 90 grams, 100 grams, and 250 torr. Dalton's law again is very easy. You have PT, total pressure, is equal to the individual pressure. So that means in this case, it's the pressure of CH4 plus the pressure of your argon. So PCH4 plus PAR should be equal to, in this case, the total pressure is 250, in which 250 torr is millimeters mercury because they have the same conversion. So you can just make that as millimeters mercury. Then, how will we be able to solve for the partial pressure of CH4 given the amount? So another equation that you need to remember for Dalton's law is about mole fraction, in which if you want to get the partial pressure of CH4, that means PCH4 is equal to the mole fraction CH4 times the total pressure, correct? But how do we get mole fraction? Mole fraction, again, this one is from your amount, your 90 grams and 10 grams. But because it's mole fraction, you need to convert first your grams to moles. So let's convert it individually. Let's start with methane. Mole fraction of CH4, let me just put the formula here, if it's mole fraction. That means you need to get the mole CH4 total moles CH4 plus argon. You need to convert your grams. Again, please use your periodic table. Let me just put the conversion here. 90 grams of CH4 should be divided by 16.05. So that's 19.05. That's your molar mass CH4. So that's going to be equal to 61. 5.61 mole CH4. For the 10 grams, that's 10 divided by, that's 10 divided by 39.5. That's the molar mass of your argon. So that's equal to 2 decimal places only. So 0.25 mole argon. So knowing this, we can already substitute that. So partial pressure of CH4 is now equal to mole CH4, which is 5.61 total mole. So total mole is still 5.61, but add the other mole of argon, 0.25. So that's the entire formula of mole fraction times the total pressure of 250 torr. Okay, so 5.61 divided by the sum of 5.61 plus 0.25, then the quotient of that will be multiplied to 250 torr, 239.33 torr, or that's going to be replaced by the unit millimeters mercury. That's just the same. So again, the point here is, in Dalton's law, you can always associate your partial pressure to mole fraction. And when we talk about mole fraction, it should be the mole of that substance you're looking for over the total moles of everything that comprise the mixture. Okay, so mole, not grams. So your grams, just like what we did here, has to be divided by the molar mass of the compound. So after dividing by the molar mass, you get the mole, then you substitute that in the mole fraction before you multiply that with your total pressure. Okay, so two things for Dalton's law. Two things. First is the basic definition of Dalton's law. total pressure is the summation of the individual pressure of each substance in the mixture. And another one is to get the partial pressure of a certain component that should be equal to the mole fraction of that component times total pressure. That's all. That's all for Dalton's law. That's all you need to remember. Okay, that was it possible to have Dalton's law that's associated law? Yes, it's very possible. How will you know? You will know that if you have other values given. Like for example, in this problem, you may be given temperature and volume. So that means it's a hint that you can use ideal gas law. Okay? So just be mindful of what you're solving, what you need to solve, so that you can get what is unknown. Okay? Any questions so far? For me to recall four more problems related to Dalton and some ideal gas law and Graham's law, just to be able to review you further. Okay, so that's it for the tests. That's it for the test. I hope that your test paper is full of corrections right now, and so you can go over review tomorrow or tonight. Let's now go to this. Okay, let me use another color this time. Okay, here. It takes 243 seconds for 0.0000446 mole diffuse through a tiny hole. Conditions, how long will it take 0.000446 mole neon to effuse? Now, some problems you can just simplify that. What do you notice with this problem? Can somebody answer me? It's the amount, correct? It's amount. So that means I can just simply simplify that because the amount is the same. Now, what type of problem am I dealing with? Because it's about diffusion, this is about Graham's law. What is the expression of Graham's law? The V of a certain gas, in this case, XA is mentioned first, so that's XE first here. V of XE, or the rate of XE, over the rate of the second gas neon is equal to, so the ratio of the two gases is equal to the square root of the mole ratio of the inverse of the gas. So because Ne is denominator here, that means we're going to put numerator for molar mass. And that's over molar mass of Xe. That is the basic equation for Graham's law. Conventionally, whatever is the gas mentioned first, that's what you put in the numerator for the rate, and it follows everything. And remember, if it's the square root of, it's the reverse. If Ne is here, it should be numerator on the right side, because mass and rate are inversely proportional. The lower the mass, the higher the rate. The bigger the mass, the slower it escapes through the hole. So, how do we define rate? Rate was defined, the V here, the V is defined as amount per unit time, correct? Which is the same as Ne, amount, but it's Ne per unit time, which is still equal to the molar mass of Ne, which you can go to the periodic table. Molar mass of Ne is 20. And molar mass of Xe in periodic table is 131.29. Now, what do you notice again? The amount are just the same. That means you can just cancel them out. Amount is N. So we're left with, this is 1 over Txe and 1 over Tne. You want to simplify that. That's going to be reversed into Tne over Txe, in which you are asked for the T of Ne. You're asked for this, and you're given TXE, which is, let me put that there, 243 seconds. And that's equal to the square root of 20.18 over 131.29. Okay, let's see if you know how to derive that. Can you please get your calculator of your answer for the time of Ne? Now remember, if it's Graham's law, never ever forget and ignore your square root. Never. So add first, divide first, 20.18 divided by 131.29. After getting the quotient, you need to square root it first. And after square rooting that, you know that you can already multiply that to 243 seconds. You can get TNE. Please give me your answer. Miggy, don't forget to multiply it to 243 seconds. So divide 20.18 divided by 131.29. You square root that, you get 0.39. And what do you do after 0.39, Miggy? You still have 240. So times 243. So TNE is equal to, correct, 95.27 seconds. That's the correct answer. Because you're just getting TNE. So that means the TXE has to be considered. Thank you, Bea. Yes, Daniel, can you just wait? We're having gas loss for a while. Let us just finish all gas loss before organic chem. So we have 95.27 seconds. Now, let's check whether we got the logical answer. Now, between Ne and Xe, Xe is heavier, right? Xe is heavier, and so Ne is lighter. So it means if it's lighter, it should travel faster. If a gas is lighter and it travels faster, the time has to be shorter, correct? So that means our answer is logical because 95 seconds is shorter than 243 seconds. Okay, so that's logical. Again, if it's lighter, it's faster. If it's faster, that means the V is higher in that case. But since we're dealing with time, it should travel faster. So time is shorter if it travels faster. If it's heavier, like Xe, if it's heavier, that means it travels longer. So the time is longer. Okay. Question. That's Graham's law. Let's have the last for Graham's law. Look at the problem. What is the rate of effusion for a gas that has a molar mass twice that of a gas that it fuses at a rate of 4.2 mole per minute? Approach this problem. It's a gas, that means it's a known. It's an unknown gas. Rate means V. You're asked for the V. So what is the rate of a gas X, which we don't know? That gas X ko no, the molar mass of that unknown gas is twice, sorry, let me just make my equal sign correct. Does it look good? Okay. So Vx is a known, and then the molar mass of Vx is twice that of a gas, that of another gas. That means we can just make that as of A. That of a gas, so that means that of a gas that I'm talking about in the problem, that the problem is talking about, that diffuses at a rate of 4.2 mole per minute. Okay? And so what's the molar mass of that of a gas? If it's just molar mass of A, so we can just make it variable because we're not given any of its identity. So we can just make molar mass of A as molar mass of A. And the gas that's unknown has twice of this mass, so 2 times molar mass of A. We come to think about it, it's cancelable. So it's not that hard. All you need to do is be able to make the right relationship. And so because gas X is mentioned first, so when we make our Graham's law equation, it's going to be Vx over Va. By the way, you can use any letter, okay? X or A, X or Y, it depends on you. So V equal to square root of molar mass of A over molar mass of X. Molar mass. And we know Va. So Vx is a known over 4.2 mole per minute is equal to molar mass of A is just molar mass of A, while molar mass of X is 2 times molar mass of A. So you can cancel that out, and that's going to be reduced to 1/2, correct? Calculator. You 1/2 is just 0.5, then you square root it. So you can just get Vx. So Vx is now equal to 4.2 mole per minute times the square root of 0.5. Correct? Give me your answer, please. Can you please comment? What's your answer for Vx? So Vx, what's your guess? Should it be higher or lower than 4.2? Should the rate be slower or faster? The answer should be 2.97 mole per minute. I hope you guess it right. X should be moving slower because it's heavier. Correct. Bea, Cherry, and Miggy. Now, our answer is logical because we said X has a mass of twice the molar mass of A, so it's heavier. So if it's heavier, no Miggy. If it's heavier, it should be slower. So 2.97 less 4.2. It makes sense. 4.2, that means that's your gas A. Gas A should travel faster because it's lighter. Okay? So 2.97 means it should travel slower because it is heavier. It's double the mass. Okay? It's different with the time. V is not the same with time. Time, if it travels faster, time is short. But if it's about rate, if it's heavier, the rate is slower. V should be slower. Okay, question so far. Now we're gonna go to Dalton's Law. Okay, so please absorb that for Graham's Law. And again, for those who are watching this in some other time, I hope you are really taking notes and answering this on your own, so that you can really experience it. That's how you learn, when you get the experience. Okay, let's go to the next problem. Is about the total pressure of the gas mixture is 1. So this is an idea of a Dalton's law because it's gaseous mixture and total pressure. So this is about Dalton's law. N2 and O2 is known to contain 0.05 N2 gas that has a temperature of 298 Kelvin and a volume of 2,000 meters. Pressure and the number of moles O2 gas. O2P, the internet is kind of, so Pn2 plus PO2, in which the total is 1 atmosphere based on the problem. So if we can get N2, then we can get O2, correct? So that means we pay attention to N2 first, in which you're given temperature and volume. This is what I'm talking about. If you're asked for T and V, that means you can use ideal gas law, correct? And the only thing that you need is the pressure of N2. So let's get pressure from PV is equal to nRT. So P N2 is therefore nRT over V, in which the N of N2 is 0.05 mole times 0.0821. Put the unit, let liter atmosphere per mole Kelvin times T, sorry, my space is not enough, so let me just put it here below. So that's gonna be 0.0500 mole times 0.0821 liter atmosphere per mole Kelvin of 298 Kelvin, no need to derive, over V, which is 2 liters. So let me just transfer the equal sign. Equal sign has to be here, align with your dash, with your over sign. So we can get now our pressure of N2 to be 0.612 atmosphere. Now we can get the pressure of O2 from here. 0.612 atmosphere plus PO2 is equal to 1 atmosphere. So PO2 then is 1 minus 0.612. So you'll get an answer of 0.39 atmosphere. So we got the first unknown, 0.39 atmosphere. Next is, how do we get the moles of gas? Now this is the reverse now. We now go back to our ideal gas law, in which N is equal to PV over RT. Mixture, they should have the same temperature, volume, and pressure, volume. I mean, the pressure we'll use 0.39, but the volume and temperature has to be the same. So we'll put the pressure of O2, because this is N, use 0.9 already, times the liters over 0.0821 atmosphere Kelvin of 298 Kelvin. So in the calculator, we're gonna get N of O2 to be, what's your answer? I hope you get an answer of 0.032 mole. So that's how we get the two unknown of that problem. So N and P. Again, it should be exclusive. If you're using ideal gas law for Dalton's law, that means it has to be exclusive. If you're looking for the pressure of nitrogen, that means the exclusive is the amount of particular gas. If you're getting the N of a certain gas, that means the exclusive there is the pressure. Temperature are shared for all the components of the gas mixture. Okay? So remember the exclusivity. And lastly, let's go to the last. We go to organic chemistry. This is about the chemists. And I think I've given you this problem before in one of our seat works in the classroom. So this is a chemist that synthesized a gaseous compound made of chlorine and oxygen and finds its density to be 7.71 grams per liter at 36 degrees Celsius and 2.88 atmosphere. Calculate the molar mass of the compound. Density and molar mass. What do we remember about density and molar mass? Density again, what's the formula of density? According to ideal gas law, it's P mm over RT. And since we're asked for molar mass and we're given density, so when we derive this, that's over 1, cross multiply, so that's dRT is equal to P mm. The mm, so to get rid of the P, that means that's divided by pressure. So molar mass then is equal to density, which if you look at the unit of density, it's already grams per liter, so that's correct. Unit of density, 7.71 grams per liter, times the R of 0.0821 Kelvin, of 36, but it should be in Kelvin, so you need to add 273.15, so that will be Kelvin divided by your P, which is already in atmosphere, so that's correct. That's 2.88 atmosphere. Let me just transfer my equal sign here. Okay, so molar mass. Inputting that in your calculator, my molar mass looks dirty. Let me just make it nice. So molar mass, input that in the calculator, 7.71 times gas constant, 36 plus 273.15 divided by 2.88 atmosphere. Mass is now equal to, what's your answer? 67.95 grams per mole. Then that can be like the exam. You may be given choices of compounds and you need to know its true molecular formula. So just be able to know that since you got 67.95, check your choices if ever there's a compound that has the same, more or less, very near value to 67.95 grams per mole. Okay, so again, C is equal to P mm over RT, in which you can just derive the formula, whatever it is that you need to get. So that's it for ideal gas law, Dalton's law, and Graham's law. About gases before I proceed. Organic chem. Organic chem will just be short, and I have good news for those who are listening to me right now. Sorry. Okay, any questions so far? May I see some questions from you? Questions? Arancha, any questions? Any questions? Okay. I think it's time for us to do organic chem. Okay. Are they the same? This is organic chem. This is analyzing structural formulas. Thank you for the reply, Arancha. Okay. I hope you're ready for gas laws. Again, I promise you that for gas laws, it's just going to be ideal with density, of course, Dalton and Graham's law. The rest will be conceptual. So you just have to know the variables. That's why we review the variables. Okay. So let's look at structural formula now. There's a question here. Are they the same? When you say are they the same in terms of molecular formula? So let's analyze skeletal structure again by putting in the right carbon for all the structures that were given 5. So remember, each tip means carbon, and then you supply how many hydrogen per carbon. So let's do carbon first. That's the protocol. You do the carbon first so that we won't commit a mistake, okay? So every tip is a carbon, so this is carbon, another carbon, 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 and carbon. We do the others also, okay? So this is C, another C here, another C, C, C. And here this is C, 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 C. And for the last two, we have C here, C, 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 and C. And here also C, 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 C. I want you to observe first the number of carbon. How many carbons do you see in all of the 5 structures? Please reply. What do you see? How many carbon here? This is a C. It's a, I'm waiting. 6, correct, Cherry, C6. This is also a C6, correct? This is also a C6. This is C6. And this is also a C6. Correct. Let's supply the hydrogen. So we'll know the hydrogen. Let me use blue. There. Let's start with the first. We need to put 3 hydrogen. We'll just make it condensed for now, okay? We need to put 3 hydrogen. In this case, we need to put 2. In this case, we need to put also 2. We need to put 2, 2, and 3 because it's a single bond. Correct? For the second one, we need to supply H3 here. Correct? Not congested, so that's why I place it on the left side. This one is a CH3. This is a CH only. This is a CH2. This is a CH2. And this is a CH3. Correct? And for this, we need to supply 3 more. Here, we need to supply 2 more. This, we need to supply just 1. This one, we need to supply 3. This one, we need to supply 2. And here, we need to supply 3. For the last 2, we have to supply 3 here. We need to supply 1. This one, we need to supply 3. And here, we need to supply 1. We need to supply 3. And then 3 as well here. And for this case, we also need to put 3, a 3. And do we need to put anything here? No need, because that's just 4 already. This one we need 2, and this one we need 3. Okay, now I want you to view that and let me know how many hydrogen per structure we have. If we count the first structure, this is 3 plus 2, 5, 7, 8, 9, 10, 11, 11 plus 3, we have H14. Correct? Here, second structure, this is 3, 6, 7, 7 plus 4, 11 plus 3, it's also CH, a C6H14. Here, this is 3, 5, 6, 9, 9 plus 5, it's also H14. Here we have 3, 6, 7, 8, 8 plus 6, that's also H14. And here last, that's 3, 6, 7, 7 plus 3, 10, 6, 9, 9, 10, 11, 11 plus 3, that's 14. So what do you notice? What do you notice? In all these structures, molecular formula, but their line structure is different. How are they different? Through branching. But but even if they're branching out, it doesn't mean that the molecular formula changes. Now, the fact that you have the same carbon and the bonds are all single bonds, it's one of the examples that your compound will not change its molecular formula. It's gonna just change the way it's being arranged, which is its structural formula. So I hope that with this simple skeletal structures, I am guiding you on how to how many carbons and how many hydrogens we're going to supply. If in case you will be asked to give the condense, so the condense will look like that. You may remove the lines already. So you may just like this. If I'm going to make the condense of this, it's going to be CH3, 2. But if you count how many CH2s you have, that's 4. So you can just shortcut that as CH2, 4, and then CH3. That's your condensed structural formula for C6H14 with lines. If it branches out, then you may just write the branching out to be like this. So this is CH3, CH2, let me just move that, CH, and then there's a branch CH3, you may put that as a parenthesis, then CH2, CH3. Or you may just write this, the branch as a specific branch really, CH2, then CH because it's connected to CH. So you may just write the branch as like that. And then CH2, CH3. Okay? So this is your option if you're gonna write a condensed structural formula for branching out. You may put it in parentheses or you may put it like really a branch in the condensed structural formula. If there are many repeating chains, a continuous line structure, you may also group them. Because they're the same straight CH2s, then you may still also put a parenthesis and put a 4 as to how many they are. Okay, so that means it's a segment. You're not changing the segment. Okay? Branches of the other structures, you may just do the same as to how I've shown you with this. So if there are 2 branches, that means you can put 2 branches for the 2 CHs. You may put parentheses after every, or you may put an extension in the condensed structural formula, which is the same as this also. You may put a parenthesis or you may put it as an attachment, up or down. So again, there are 4 ways of representing your organic compounds. It can be through your molecular formula, the condensed structural formula, which is this, the line structure, or the expanded structural formula. The expanded is, you'll just extend the H. That means you draw a line for the H so that it will complete your 4 bonds of H. Okay? So please do not confuse yourselves with that. And again, always remember that for the 4 elements involved in organic compounds, hydrogen should have 1 bond, oxygen should have 2 bonds, nitrogen should have 3 bonds, and of course, carbon should have always 4 bonds. Nothing more, nothing less. Nitrogen and oxygen, you can distribute the 2 and the 3 bonds, either triple bond, double bond, or all single bond, as long as there's 2 and 3 for both. Okay, for each of them. Okay, last. Where's my last item? I have a last item for you here. Here. We give the condensed structural formula of this skeletal structure. Now, again, the technique is you please put the carbon first. You put the carbon first so that you'll know, because this is condensed. So that means we need to put carbon first. So you put carbon for every intersection, for every tip. Don't miss any of the tip. Okay? There. So, after putting all the carbon, then we can put all our hydrogen. Start. This H should be H3. H3. That's a CH2. CH3. This is a CH3. This is H2. This C don't need any more H because it has 4, 1, 2, 3, 4. And then this one is H3. This is a CH2. This is a CH. This is a CH2. This is a CH3. And that's a CH3. Okay. So, how do we write this down? Now, you can have options here. You may, because there's so many branching out, it may be that you can choose the longest structure. The longest structure, for example, when we say longest structure, you can choose the longest straight line structure so that you'll know what will branch out. In this case, if you look at the longest structure, it's going to be like that. This is your longest straight line structure. That's your line. That means the rest that are not involved are considered your branch. So if you wanna write down the condensed structural form, then hello, hi Sir Christian. I'm doing live streaming. Sorry, Vites, but it's okay. So if you're gonna do the longest, if you're gonna make the condensed structural formula of the structure, so you may just put the line first, the straight line, so that's gonna be CH3, CH, then CH, then CH2, and you have C, and after C, that's your CH2, then that's your CH, then CH2, CH3. And then you put where the branches are. In the second CH, you have a CH3, so you may just put that there. In the third C, you have a branch of CH2, CH3, so you may just put that there. And then in the C here, you have 2 branches, so you may have put CH3 there. You put another CH3 there. That's correct. And then in the third from the last, the CH here, you have a branch of CH3. So that's the most organized thing that you can do if ever you'll be asked to draw the condensed structural formula of a very lengthy organic compound with so many branches. That I suggest that you just have to locate the longest chain, straight line, continuous CH chain, so that you'll be able to identify what's your branch. Okay, now a longest chain, that means it's continuous. You can't bend. So in the continuous, this includes here. It's still continuous. We just bend it because if we just go to CH3 as the longest, it's not longest because this is the longest because you still have 2 carbons. In this case, you only have 1. So that means after CH, it should go up there, not going here. That's why we go all the way up. So that means this one is a branch then. You can't bend and then go on there. No, it should be straight. How you do your condensed structure. And if you are to get the molecular formula, just count how many carbons you have and how many hydrogens you have. Formula. Okay. And in the exam, for Daniel's sake, in the exam, I placed the correct answers. Anymore, discuss it in the live stream. The second to the last exam that we had on drawing the skeletal structure and the condensed structural formula, I took most of the papers, so that means you just have to do it on your own. That's how you will learn. So I'm just giving you a glimpse of some reminders for some you need to do tomorrow. And Aryan just asked me for the types of tests. The types of tests, I have told you it's the same types of tests that I've been giving you. Mysterious test item, problem solving, doing the structural formula, expanded, condensed line structure. There's nothing new. It's all the same test type. So you need not worry anything. Do you understand what you're supposed to do? You need to be able to analyze properly on how you must be able to answer a certain problem or a certain challenge in the item. Okay? That's the most important thing. Good news before I end this live streaming. For the good news tomorrow, you're not gonna be tested about functional groups anymore. I hope you're clapping your hands right now. So no more green paper. All you need to have in your mind right now will be the gas laws. That's all you need to remember. And of course, organic chem, which is easy. You're used to that. So, final, no more green paper. No need to memorize the functional groups. I promise you that. Just focus on your gas laws. Focus on organic chem stuffs, which is the definition of terms and all. And of course, all the 4 representations of organic compounds. That's it. I hope that I have helped you in your preparation for Gen Chem tomorrow. Please be ready, focus, analyze, think. Do not attempt to cheat. Do not attempt to have the easy way out. And I tell you, it's worth the hard work, it's worth the persistence, it's worth the thinking. We never give up thinking. You are STEM students. You should not give up. What I have told you, never give up and never stop learning, unlearning, and relearning. So continue studying with your notes, and you can still continue to watch this video all over again in case I was too fast with the discussion. Now, this is Madam Narca. Again, saying no need to memorize this 18 functional groups for tomorrow. No need, no green paper, just gas laws, and study everything that you've answered in the seat work and everything in the exams. So that's it for now. Bye-bye. God bless you all. Again, never stop learning, unlearning, and relearning. God bless you all.